UVCE Chronicles, sing it loud. Echoes of our past we're proud. From the heart of Bangalore to the world we soar.
Hello everyone, welcome back to another episode of UVCE Chronicles. And my name is Sohan Aiyappa from Electronics and Communications third year. And today we have an extraordinary guest, Professor K T Ramesh, who graduated from UVCE from Mechanical Engineering the year of 1982 and currently a very leading and esteemed professor at Johns Hopkins University in Mechanical Engineering. Sir, it is a great honor to have you with us today. And one of the world's leading scientists in the area of extreme materials, and it is a fact of honor that the person like you has graduated from our college. It is something that inspires all of us. Welcome to UVC Chronicles.
Great. It's great to be here. So, great thing that you guys are doing. I really like this idea.
Yeah, thank you, sir. So, could you, to begin with, could you please briefly introduce yourselves to our listeners?
Sure. So, my name is K T Ramesh, Kaliat T Ramesh, but I go by KT. I've always gone by KT. Um, I graduated, as you said, from UBC in 82, went to IIT Madras for a year, and then I went to Brown University. And then from Brown, did a PhD there, and then went to the University of California in San Diego, in La Jolla, a beautiful place. Stayed there for a year and then came to Johns Hopkins University. So I've been here at Johns Hopkins for 37 years now. It's a long time.
Yeah, that is a very long time. Indeed. 27 years is almost twice of my entire lifetime. So,
That's right. Yeah.
yeah.
And I guess just to maybe ground things, I've remained in engineering throughout my career. So I started as a mechanical engineer, and I'm still in mechanical engineering. So my department here is the Department of Mechanical Engineering, although I do a lot of other things.
Yeah. Sir, so you graduated in the year of 1982, and from the what you told previously, there's a lot of things that happened after that. Could you pick one moment or a couple moments that put you on the path that you are on today? That happened in when you while you were at UC.
Yeah, sure. Actually, there were a number of them. And some things set me on the path, and some things sort of kept me straight, right? So, in terms of setting me on the path, so I had a number of really good professors, but the one in particular that I would call out is Professor Yalaradi, so T. Yalaradi, who is still around, and I think comes to UBC occasionally. He was teaching us mechanics, essentially, strength of materials in that area. And I really enjoyed his courses. He encouraged me to think about research. And then we did a senior project where he was the advisor. And so that really got me onto this path. So up to that point, I handled the courses well, the classes well, but I wasn't particularly excited. But he got me excited. So that's one thing. And I guess the other thing I should say, one thing that really made a difference to me was the group of friends that I had when I was in UBC. My classmates were really good, really nice people, but also very encouraging. So that combination made coming to college a lot of fun.
Yeah, definitely. I mean, even for us today, our peers are a great source of motivation today also. And yeah, I mean, personally for me, I found mechanical engineering really interesting, but then I decided it was something that I didn't find it easy. So that's why I shifted to electronics because somehow more easier for me to visualize circuits than visualizing physical stuff. But it definitely is a very interesting space. Sir,
Yeah.
also another,
I guess I should also say, I think mechanical engineering then and mechanical engineering now are a little bit different, right? So
yeah.
things have changed for you, and the same with electrical engineering. It has evolved a good deal. So you see a different landscape than we saw.
Yeah, very much different. So, like something that I usually ponder about a lot is the fact that engineers in that time did not have that tools like CAD tools and everything that makes our work easier today. And it just
Mhm.
makes me think about how much effort they had to put doing everything on paper. It sounds like a very difficult task.
That's true. So we had to do everything pencil and paper. And what that did was it forced you to be very efficient with your mind, right? Because you can't spend too much time at it. So it meant that if you had a better understanding of things, you were more effective. You cannot use a brute force technique. And maybe just to help your colleagues recognize the time that I was in, at that time, there were no computers in the traditional sense. There was a tape-based analog computer in UVCE. That was the only computer at that time. We didn't even have punch cards.
Yeah,
I saw Hollerith punch cards only when I went to IIT Madras. So things have changed a lot.
yes, yes. It has made things easier for us. It also has made us dependent on the tools a lot more than what we need to be.
So, yeah, this is, I was dependent on a calculator. You're always dependent on something.
Yeah. So another interesting fact that I found about you was that NASA has named an asteroid after you. I think it's 32518 K T Ramesh. So how did that come to happen, and what did that recognition mean for you?
Yeah, it's not with what it means for me personally. For me, it was very nice to get that recognition because what it
Yes.
says is that the planetary science community recognizes the work that I do. So that was very nice. How I got there is actually a really interesting story. So I'm a mechanical engineer. And, I started out in traditional mechanical engineering, and one of the things I studied was impact, right? I still study impact. So how one thing hits another. And it turns out that impact is a big problem in the solar system. So you get asteroids that are being impacted by other asteroids all the time. You see craters all over the planets. You see craters on the Earth. So I began to study cratering. And that's how I got into the planetary science end of things. So still doing mechanical engineering. I'm just doing it at a much larger scale.
Oh yeah,
And so, and the way it happened actually is kind of interesting because I did not even know it was happening. So, one of my former, I don't know exactly how it happened, but I think one of my former students or postdocs actually nominated me, and that went through the process. So, you get named by the naming is done by the International Astronomical Union. So, um, that was very nice.
yeah. I mean, it must have been a wonderful feeling to wake up one day and know that NASA has named an asteroid after you.
Yes, yes, it is wonderful, and it's the kind of thing that most people, do think it's a big thing. But there are lots of asteroids, so there are lots of things you can name.
Yeah.
One interesting thing, just so your listeners know, uh, we do not allow the naming of an asteroid after a person, after a living person, if there's any chance that the asteroid might hit the Earth. So I can guarantee you that the asteroid K T Ramesh will never hit the Earth.
I mean, it's good to hear that you feel a bit safe now. Um, so yeah, so another interesting thing. So when Adrian was trying to reach out to you to join a podcast, he noticed. I mean, we noticed that that you have an AI assistant that sends your emails and interacts with us. So, I mean, I found that really fascinating because I've never seen anything like that before. So how did that happen? So like, and how does it help you that AI tool?
So this is an AI agent, basically. It does scheduling, and it's actually a really useful device. So just to give you a sense of my life, I meet a lot of students. I teach classes, some big classes. I have a number of research students. So I'm constantly meeting people. And I always get emails about, can you meet for this? And can we talk about that? And so forth. Scheduling my calendar is always complicated, right? So usually you have this story where you want to meet with me. I send you an email and say, can we do this time? You say, no, I can't do this time. Can we do that time instead? Then I look at that and say, well, somebody else asked me, can they meet at this time? And I don't know what they're going to do it yet. It gets complicated. It's a difficult problem. So for many years, I've had a member of my staff do this for me because I'm just not good at doing it myself. When I do it myself, people get upset because they don't get to meet me often enough. Uh, and then about a year ago, I started looking into these agents, and this particular agent, essentially all it's doing, it can see my calendar, and it then does all the communication with whoever is trying to get uh, a meeting in. It has the authority to place meetings on my calendar, and it's smart enough to be able to say, well, look, this meeting is slightly more important than that meeting, and to move them around. So I've been very impressed. It's also very cheap. So very
Yeah.
effective tool.
It is very effective. Like usually when we try to call in a guest, it usually takes about a month or sometimes a couple months. But with you, it happened in less than a week. So it is extremely efficient for both parties involved.
Right, right. It's also something that my staff tell me they really don't like doing. It takes too much time for the human, whereas for the machine, this is really simple.
Yeah. Also, sir, for someone hearing about it for the first time, how would you describe the Ramesh Laboratory at Hopkins University, and what kind of work do the students in the laboratory do?
Yeah. So happy to talk about that. In fact, one of the things I will say, I'm hoping that I can get some students to come from UVCE to my lab. That would be great. It's been a while since that has happened. But yeah, so my lab is kind of a broad lab, meaning we have a number of different things we work on. We work on mechanical engineering impact problems. We work on material science problems. We work on problems in planetary science, problems in biomechanics and brain injury. And so what that means is we have lots of applications, but the kinds of things we do are quite similar. So the basic equations are actually the same. What we're doing is looking at those equations for different problems, for different applications, often different scales. We do both experiments and lots of computational modeling. I like the experiments a little bit more, and I enjoy the experimental side. We do some theory, um, but these days you can't do anything useful without doing some computational modeling. So that
Yes.
combination of doing both the experiments and the modeling is really valuable. My group is maybe, I think right now it's 6 graduate students and 5 postdocs. So a graduate student is someone working towards a PhD. A postdoc is someone who has a PhD and is going trying to become a faculty member. And usually that's the kind of ratio of people I have. Some of my students do experiments at high velocity impact. Other students do experiments on biological organisms, on bacteria. So there's a wide range of problems we look at. The way I think about it, I look for people. So if I can find somebody that I can work with well, then we'll figure out a research problem. That's sort of the approach I take. I don't start with the research problem and look for a student. I start with the student and I look for a problem.
Yeah, that's a good approach. I feel more creativity there. So all your time in the lab, which particular project that you felt had the most impact? Pun intended.
That's so hard to say. It's like asking for who's your favorite child. You don't have one. You like them all. Some are easier than others, for sure. Um, but the impact is really better assessed by other people, not by you, when you do the work. Because often when you're doing the work, you're doing something fundamental. You don't know how people are going to use it. But I'll give you 2 examples of things that I think have been kind of fun. One is in materials. So I developed some ways of thinking about nanomaterials and how they might behave. And at the time we did that, it was a nice fundamental problem, but now I see lots of people use it. So that's been exciting. There's lots of engineering applications of these kinds of things. Another one is with respect to uh, the fracture of materials, the breakage of materials. So I was interested in that originally from a simple engineering viewpoint. When will, I build a bridge, when will things break? Or I have a piece of body armor, when will that fail? But that idea, the way in which I work with it, turns out to be also useful in planetary science. It turns out to be useful in mining. It turns out to be important in when you think about volcanoes and the dust that you form. So lots of applications from something basic. So those are 2 really exciting things. And maybe more recently, the work we've been doing in brain injury, that has been used by a number of people. So I'm generally think of impact as if somebody's using it. So,
Yes. Uh, so, I mean, at this point that we know that your lab and the research work that you yourself have done, even though the core idea is something that is mechanical, the application is in so many diverse fields. Um, as an engineer, what requires you to think that in that perspective? Like it is easy for to take say a concept as simple as fractal modeling, but then what does it take for a person to start thinking it and applying it in different ways, like as examples that you gave, as was it armor and then volcanoes and then planetary science. So how does that happen? How does it go evolve from a theory to such a huge and diverse application?
Yes, that's a really good question, really perceptive question, actually. And the way I think about it, I think the way this works is, we engineers are really good at analyzing problems, right? You take the bigger problem and then you break it down to smaller problems, and then you try to solve the smaller problems. That, that way you can solve the bigger problem. And then often many of the smaller problems have already been solved by somebody, and then you find this one piece that hasn't been solved, and you fix that, and then you bring everything together. That's how you solve the big problem. So a lot of the ways in which I've ended up in so many fields is because I bring that engineering mindset to these problems, right? So let's say I think about in planetary science, I'm thinking about asteroid disruption. So I think about that as a big problem, and then I ask, okay, so what controls asteroid disruption? Well, it's the strength of the rock, and then how hard you hit it. And what controls the strength of the rock? Well, that's the fracture of the rock, the cracks in the rock. And what controls crack growth? Well, okay, that's fracture mechanics. All right, so if I can understand fracture mechanics, then I can build up to what happens in an asteroid. So that's typically the way in which we do things. We start with a bigger picture, and then we try to identify the fundamental mechanism inside that application. And often you find these fundamental mechanisms are the same or very similar. So the same idea that I'm using for planetary science, I can use for ceramics on Earth. One place where things got really different is in biomechanics. In biology, the mechanisms tend to be very different. And so that's a much more complicated space to work in because you have to learn the language of the biologists, of the doctors. And we in engineering, in mechanical engineering, we don't usually learn that language. So that takes some time. And the real thing that happens for people like me is that students come in and the students and I learn together. And so in many ways, the student is teaching me about the biology as we go. And by the time the student graduates, the student definitely knows more about the problem than I do. So this is the way in which you build your way through it. And throughout, as many students come through, you learn more as a person.
Yeah, that's definitely very interesting, sir. Like that, I feel like that's something that we, as a student, is something that we're like completely unaware of. The concept that we learn in theory, which in many ways seem boring to us when we sit in the class, and it has so many diverse applications everywhere. And I feel like the subject would be more interesting if we are also putting our hands and applying stuff and being creative with.
Right, right. I think that's an important thing. Actually, we were talking about Professor Yalaradi. That was one reason he got me excited was he could draw that connection between the basic stuff we were doing in class and the application. Right? He drew that thread out, and then you could see that what you were doing was valuable. I think that's a good teacher if you can make that connection in each
Oh
case.
yeah, yeah, very definitely, sir. And in electronics, the subject that we have something called signal processing, which is to many people seen as a hard technical theory-based subject. I mean, syllabus-wise, it's mostly maths. But then we had a professor called K D Raja, and he explained the concept in such a way that I used to see that technology happening whenever I was maybe looking at a phone or that communication part of it. And
Mhm.
that really excited me a lot in communication technology. And I believe that that perspective is what makes us engineers.
Right. Absolutely, absolutely. And the thing about engineers is we like to see something happen at the end. So
Yeah,
that seeing things through to the end is important. Getting that vision is really important.
yes, very much, sir. Sir, also, what advice would you give to students currently? Because the way here in India, at least, as far as I'm aware of, engineering has become a sort of getting placed, getting a job with a certain amount of salary. That perspective is something that a lot of students are in right now. So, what advice would you give students to, basically give more life to engineering than what it is today in India?
Yeah, so you have many really good things going for you. I think India is a very vibrant kind of economy. You have lots of uh, s- startup kinds of activity at the lower levels before you even get to the larger companies. So there's lots of creativity, I think, inside the ecosystem. Um, but maybe to get to your bigger picture question, I think as engineers, you always have to think about two things, right? At a base level, you have to make a living. And to make a living, you have to get a job, and that job has to be in a sector that is sufficiently productive, that you're likely to maintain your job, you have some growth path. That is sort of the necessary condition. You need that. You need the money to be able to manage. Um, but really, what would get you excited is if you can see that what you're doing is having an impact. That's true for most engineers. If you're in the automotive industry and you see that somebody is, you're helping build a car, and at the end somebody's driving the car around, that has an impact on you. It's the same for most of us, right? If you can see that application at the end, so your job might be this one piece that leads to that application. But if you can see people using that application at the end, that will make you happier. Sort of a broad sense of that, in my view, is not having money can make you sad, but having money will never make you happy. You have to have more than the
Completely.
money. You have to have some kind of excitement, some kind of vision, some kind of aspiration, whether that's about the people around you or the country or the industry, something that gets you excited and gets you waking up in the morning, right? Those things are important. You balance that. So early on, you spend your time, I think, establishing yourself, getting your job, getting the funding, making sure you can survive. But then you always want to keep your eyes open for that big picture. Why are you doing what you're doing? I think that will help stabilize you as you go.
Yes, yes. I feel like that's very important. Also, sir, last question. How was it like the interaction between, I mean, the environment in our college at that time? And do you think UC being a government college, the students being in a sort of in comparison to private colleges being independent, like in the sense that we are not spoon fed and we are not really babysitted, like, we are let to do what we want. And do you think that is the reason why the engineers coming out of this college are in many ways self-dependent because they learn it at the very early stage in their uh, college life. Uh,
Yeah, I think that's probably true. I think so. I don't know what the private colleges are like now, right? I haven't been following where they are, so I don't really have a good comparison for your current state. But I think, speaking of UBC itself, I think that's certainly the case. That two things happen. One is within UBC, I think, uh, and I think this is still true, right? The way you think about things, the way you're working towards a problem, that is something that is self-driven, fundamentally. I think the other side of it, and I think this is still true in UVC, but generally in UVC, you do not necessarily come from a background you're very wealthy, and so you already have things taken care of for you. You have to drive. That there is a level of motivation there that each of us has that is different from those who start from different places. So I think that does help. Um, I do think it's a challenging time for all universities, right now for all colleges, because the industrial sector is changing. The things that AIs can do is going to change what that job landscape is. And so it's hard for colleges to know exactly what they should teach and what's going to be something that gets, that can be done more effectively by a machine in a 5-year span. But I think, again, if you go back to what UVC has traditionally done, if you focus on the fundamentals, on critical thinking, those kinds of things will always work for you. So I think you're right. That's really the core of why people from there tend to be successful. I have some friends from some of the private colleges who are extremely successful too. So it's not that you can't be from those colleges. It's just
yeah.
different. Yeah.
Sir, okay. So, yeah, lastly, before we end, what advice would you give to our current students, especially in the evolving landscape of the industries with all AI tools and everything? What do you think the students should focus on right now?
Yeah. So a couple of thoughts there. One is, I think, particularly since you're engineering students, you should be comfortable with things like Python and data science and machine learning and AI, not in the sense of expecting that you're necessarily going to get a job in each of those areas, although you might, but to see them at the least as tools that you can use and understanding how the tools work. Because the tools can, if they're not used correctly, they can do some really strange things. So we need engineering students to at least be solidly grounded in the core of engineering, but also be able to use those tools. If you can do both, I think you'll be very successful down the line. Because personally, I don't think that the pure computer science end of things and the pure AI end of things is the direction for students to go. I think the really interesting stuff in the industrial sector in the human society down the line is going to be the intersection of those tools with the hard engineering problems, because those problems don't go away. You still have to build that bridge behind you. Somebody still has to get that steel in place. Somebody still has to figure out how to do all of that. And that, when it comes to critical things, if you don't have the core engineering knowledge, those things cannot be done effectively. So bring those two together is what I would say.
Yes. Yes, I feel like that's something that's not much talked about. Usually people always either use AI or don't use AI at all. That the fact that we can, as you told, combine the hard engineering problems along with
But
the insight that AI provides would probably the best outcome in our society. So yeah, this brings us to the end of our podcast. So Professor Ramesh, thank you for so much for spending your time with us. It has really been a fun time. I genuinely had a lot of fun conversing with you. And also to our viewers, thank you for joining us on this episode of UC Chronicles. We hope this conversation encourages you to explore boldly and think beyond boundaries, just as our alumni do. And sir, it's inspiring that how your journey began at UVC and grew into such immense contribution in various fields across the world. And it is a story that inspires all of us. And we also aspire to be someone like you one day. And thank you for sparing your time joining us today on this podcast.
thank you, Sohan. I've really enjoyed this conversation, and I'm looking forward to seeing what you guys do. Great.
Thank you.
And
Yeah,
bye.
yeah, bye, sir. We'll be back again with more stories from the UVCE family. Till then, stay curious and stay proud to be a UVCA. Thank you and have a nice day.